Alright, thank you all for your attendance at Advanced Process Control Short Lecture number 2. So, where we left off, we were talking about the idea of that there's a lot more behavior that systems can experience than what we see when we only restrict ourselves to linear systems. And so then that's good for people to be aware of, that there can be a lot of other types of behavior that can be seen, because then it gives you a better perspective on more restrictions that we need to put on our models. And also just being aware of that we need to talk about stability differently. We need to talk about a lot of things differently, because behavior is not just the simple linear system stuff. So, even though it's not really simple, nothing about this is simple at all, but this is more complicated than the linear system. So now we're going to look at some more things about, so the idea here for this next part is that when we have, so we were saying that you can have multiple isolated equilibria. So say these are your equilibria, they're multiple and they're isolated. Then you want to talk about stability of a given equilibrium. So we probably in undergrad control, and you can correct me if I'm wrong, but you probably have talked about linearizing the model around a steady state. Are you familiar with this? It's okay if not. So the idea with linearizing a model around a steady state is that you say it's x dot equals 2x squared plus 5x or whatever. So you would say, okay, well, near, this is probably a bad example, because I don't know, what's the steady state here? 0? 0 definitely a steady state. Okay, say I'm looking at the steady state 0, 0, or 0, just 0, because there's only one state. So steady state is 0, and then if you plug it in, it makes the right-hand side equal the left-hand side. So then we can say, like, okay, near the steady state, so near 0, x squared is a lot smaller than x. So, like, 0.000001 squared is a lot smaller than 0.000001. So this term is, like, so much smaller that almost I just have these dynamics right around the steady state, because this number is so much smaller than that one I can neglect it. So that's the idea of linearizing, where you essentially are left with only the linear terms. You can do this more rigorously by taking Taylor series, but here if we did that, we would get just a linear term. So when we look at the linearizations, this idea here of, okay, say I have a nonlinear equation like this one, this is a nonlinear system. I look at the linearization, and then I say, okay, well, near the steady state, I've just said why that seems like it should be true, that this is relatively representative of the behavior near the steady state. And then this should help me then, if it's true really, really close to the steady state, it should give me an idea of stability of that steady state. So then what we can do is we can say, okay, that's really cool. I want to know under what circumstances does this linearization give me an idea about the steady state? Because it turns out that if you just have like x squared equals 2x squared, so at this time there's no linear term here, so you don't say, oh, the linear term's dominating. So in this case, this linear term is dominating near the steady state. But here there's no linear term, so near the steady state, the fact that it's 2x squared actually makes a big deal and a big difference, because there's not something that you can default to and say, like, well, that other term's way bigger. Like, this is the only term. So there are times when, like, if we took the linearization here, it would be x dot equals 0. So then you would conclude, like, oh, there's no changes near the steady state. But that's not true. We know it's changing because there's this right-hand side. So it's not really true that you can always neglect the higher order terms near the steady state. There's circumstances when it's true and circumstances when it's not. So several things that we want to understand are essentially, when can you neglect linear terms, or sorry, nonlinear terms. When can you neglect nonlinear terms? If you can neglect them, then the question will become, what can I determine about the stability based on the linearization. Then what can I say about the equilibrium of the steady state? So to clarify what this basically means, when we talk about, is this okay so far? Okay. So to clarify what this is saying, when we say we look at this steady state here, we are trying to say stability for nonlinear systems is different than stability for linear systems, in the sense that when we have a single steady state for a linear system, oftentimes we have been considering, do all the trajectories starting from any initial conditions go to the steady state? And that was the idea of asymptotic stability, primarily the type that you would discuss in an undergraduate control class. Now, and so that is like a global stability case where essentially it was from any initial condition whatsoever, does the closed loop system act such that, or not closed loop, we're talking about open loop actually. We're talking about the case with no control so far. So does the system without control or under a controller that replaces the input with a function of the state, so like u equals negative x or something that's a function of the state, so that you get x dot equals f of x, so that essentially your differential equation would be something like this. Whether or not that means you've already changed the dynamics with a controller by adding in the control law here, or whether or not this is your open loop system with no inputs at all. Either way, we're looking at dynamic systems that don't have an explicit input dependence on the right-hand side anymore. So in this case, we would talk about this idea of stability of, from any initial condition, can you drive the closed loop state to the origin here. And then when we talk about stability for nonlinear systems, and in cases where we might have multiple steady states, then there gets to be a question about, like, okay, clearly I don't have this global idea. Because if I start here, I'm not going to go here. I'm going to stay here. This is another equilibrium. So then we talk about going very close to the steady state. So we talk about stability with respect to being some local stability, where local can mean you're very, very close. It doesn't necessarily mean local is very large. Part of what we'll be doing later in this lecture series is showing that in certain cases you can actually find what is the local region where you can guarantee that the closed loop state is driven to the steady state. But for now, just consider it being like some region around the steady state where I want to see from any initial conditions in that region, does the closed loop state go to the steady state, or does it at least stay in that region even if it doesn't go? And so you want to know, how can I tell these things from my linearization? So then what happens is, to start looking at this, we have to first understand how do the systems act when they're just linear. So we said like what our goal is. Our goal is to determine something about nonlinear systems. What we're going to do is we're trying to analyze what we can tell from the linearization. So first we have to understand what happens when we look at just linear systems, because that's what the linearizations are always going to be. So we want to understand what's the baseline before we add nonlinear terms and take linearizations. Is this okay so far?
Yes.
Okay, cool. So this means that we're going to do a system like x dot equals ax, and so this would be something like x1 dot equals a11 x1 plus a12 x2, x2 dot equals a21 x1 plus a22 x2, and we have x of 0 equals x0. So in this case, we're going to look at this idea of phase portraits. So something that I've been mentioning to within the research group has been that when you don't know how to do something, it's always good to take a simple example, or at least a smaller scale example, where you can then very rigorously determine how to do something. So we're going to look only at these two-dimensional systems where you can write like an x1, x2 plane, and see how x1 and x2 are evolving with respect to each other over time. And so if I was to plot something like this and to say like, okay, this is time 0, this is time 5, this is time 4, like 6 or something, like you would get a sense that like, oh, okay, this is how the values of the two things over time. And so you could only really do this in 2D, and you could make a 3D one where you would then look at like a third variable, but beyond that it gets pretty hard to visualize. But that's why this is one of those simpler examples that'll help you to start thinking through something that is easier to visualize. So do the eigenvalues of a matrix. So it's the determinant. You take the determinant of A minus lambda I, and then you get the like roots of this characteristic polynomial where this determinant is equal to 0. So this is probably easiest if I show an example. So I'm just going to make something up off the top of my head. Say this is 5, 2, 1, negative 1. I don't know. I've completely made that up. So we're going to say what are the eigenvalues of this matrix. So it's 5 minus lambda. So here we do A. So this is A minus lambda I. So that means that if you subtract lambda I, that's like subtracting a matrix that has zeros on these two terms and then ones on the diagonal. So you can see I just subtracted lambda off my diagonal entries. Then now I take the determinant of this. It's a 2 by 2. It's not always this nice. But the determinant of a 2 by 2 is just going to be, you multiply this by this, and then you subtract the multiple of the other two. And so now I have to set this characteristic polynomial to 0. So it's negative 5 plus lambda minus 5 lambda plus lambda squared minus 2 equals 0. So then let's see if I can factor this. Wouldn't it be awesome if it turned out to have like special numbers? And there are certain vectors where if you multiply them by the matrix, they return you a constant times that original vector. And I guess people found out those were super important to everything that we like all the starting points of control theory, essentially. So let me check if I'm going to get a ticket yet. Not yet. Still got a few more minutes before I would get a ticket. That's good. So it turns out that, so we're going to call lambda 1, lambda 2 the eigenvalues of A. Looking at these cases where there would only be 2 eigenvalues because we have 2 by 2 systems, then there exists, so this backwards E or whatever means there exists a non-singular matrix M such that X is equal to MZ. So this is essentially being some transformation where originally you have a vector Z, you multiply it by M and it gives you X. So then that means that X dot equals MZ dot, and we can get it so that Z dot is equal to M inverse X dot equals M inverse A MZ. So we said it's non-singular. That means it's invertible. We have this kind of progression here. We're going to focus in on what are different forms that we could get. So we're trying to get some matrix M that exists, but that causes this matrix M inverse AM to have one of several special forms. So this is related to things like the Jordan canonical form and stuff like that. So this matrix M is one that has to give one of the following forms. So it does exist that it will give something of one of the following forms, depending on the original form of A. But then, so one of 3 different things can happen. So either M inverse AM is equal to lambda 1, 0, 0, lambda 2. So this is in a case where if lambda 1, lambda 2 are real here. So there can be cases where you get a form of M inverse AM of this form. Depends on how these eigenvalues are. So there's certain conditions, but in this matrix I'm saying these are real. But so when you get this form, it depends on what the original structure of A was. Then another case you can get is M inverse AM where we have this lambda 1, 0, lambda. And so in this case, lambda 1 is lambda 2 is lambda, and they're real. So then that's like a structure that can also come up. And the third structure that can come up depending on the original form of A is M inverse AM equals alpha negative B alpha. And so this is in a case where lambda 1 is equal to alpha plus J, where J here means imaginary number. Sometimes people write as I, sometimes people write as J. And then this is alpha minus J B. So then what we see here is this is in the case that the eigenvalues are complex. Then they would form this matrix that's something like this. So now all the entries in this matrix are real, but they're components of complex eigenvalues. So these are the forms that are the main ones that can happen. So then we're kind of going to go through and say, like, okay, for each of these, there are specific ways that the, we call these phase portraits, would turn out. And so I'm going to erase up here. Mm-hmm. So one way this can turn out is, let's look first, we're going to look at one example in maybe a little more depth, but then a similar way of doing things would hold for the other ones. Let's go back to this one where we have it like this. So what this means, if we look at this equation here, is that in some like transformed space, so originally we had A, x dot was equal to ax. We are able to find some matrix M to make a transformation so that we get into this Z space. And now in the Z space, M inverse AM has this special form. That means that Z1 dot is equal to lambda 1 Z1, and Z2 dot is equal to lambda 2 Z2. So does that make sense from here? Mm-hmm. So then if you take these, it turns out that these have a really nice form, like separable differential equations, in the form of kind of the old types that you solve in like a first class on differential equations, basically one of the special types. So then you can do a separation of variables. And so this is if lambda 1 is not 0 and lambda 2 is not 0. Consider first that case, that these are two eigenvalues, but they're not 0 yet. Then we can separate these, and you could do the separation of variables. But then we would get here that if you start combining these two equations now, you can say like, oh, okay, Z2 is equal to Z2 0 over Z1 0 to the lambda 2 over lambda 1, Z1 to the lambda 2 over lambda 1. And so this comes from being related to the eigenvalues.